So we're back to a simple harmonic oscillator. Simple harmonic oscillator is best represented by a mass on a spring, so that you pull it out and release it, or you hit it or something, and it starts oscillating back and forth. In this situation where we first start talking about it, we'll say there's no friction, and so it'll just oscillate forever. Obviously things don't do that because there's friction involved in most cases, but this shows up in a wide variety of circumstances, in vibration in buildings, vibration in you see in atoms and molecules, in all forms of engineering. So it shows up in chemistry. If you have a diatomic molecule, the nuclei of the molecule will vibrate around their equilibrium position, and this is a pretty good approximation to what they do, at least for small vibrations. And so this is the result. What we did was the result of a force that's directly proportional to a distance. That's to say, if you pull the mass out twice as far, it experiences twice the force. Notice that means it's going to experience twice the acceleration. Simple harmonic oscillator problems have a varying acceleration. When we first started talking about acceleration, I said, most of the cases will be constant acceleration, but not so for the simple harmonic oscillator. So we ended up with an expression that looks like this: mass times acceleration, d squared x over dt squared is the acceleration, is equal to minus kx, and we wrote that, we rearranged that and got d squared x over dt squared plus k over m times x is equal to 0, and then we said omega squared is equal to the square root of k over m, and this equation became d squared x over dt squared plus omega squared x is equal to 0, and that at the end of the day gave us this. So A is the amplitude that we talked about. Omega is the angular frequency. It's defined up here. Sorry, this isn't omega squared. This is omega. Omega squared is k over m. So omega is the square root of k over m. Phi naught is the phase, which we talked about in the video from GeoGebra. This quantity is what allows you to make this function look like a sine or a cosine or anything in between. And so for a typical problem, A and omega and phi naught are all constants. They don't change for the sake of the problem. Again, omega depends on the stiffness of the spring and the mass. So if you have a larger mass attached, you'll have a smaller omega. It'll take longer to oscillate, right? If you have a stiffer spring, you'll have a larger omega. It'll oscillate faster. And so now that we have this, we can say, well, look, from this we can calculate the velocity, right? It's oscillating back and forth. If we want to know its velocity as a function of time, that's just dx dt, which is just the derivative of this quantity with respect to time. Again, a, omega, and phi naught are all constants. The only thing that varies is t. And so the derivative of this is really just the derivative of sine of a t function, a sine of a t variable, right? And so this becomes a cosine, because derivative of sine is cosine, omega t plus phi naught, times the derivative of what's inside the parentheses, which is just omega. So that becomes omega a cosine of omega t plus phi naught, like that, right? And so this is just a cosine function, and this is just a sine function. Notice the cosine varies between -1 and 1, just like sine does. The maximum velocity is just omega a. It can be plus or minus, but the maximum value cosine can have is 1, and so the maximum value the velocity can have, even though it's varied as the object sloshes back and forth, it varies. Its maximum value is the angular frequency times the amplitude. And of course, when cosine is 0, the velocity is 0, and that's going to be at the two extremes, right? When it comes all the way out as far as it can, its velocity will be 0. When it goes all the way in as far as it can, its velocity will be 0. When it's right in the middle, that's when your velocity will be this. It'll be either plus or minus depending on which way it's going, but its magnitude will be that, right? Now that I have that, I can also calculate the acceleration, which varies with time. And again, it's it's just going to be the derivative of, in this case, a cosine function. If cosine is negative the sine, so I'm going to have negative omega a sine of omega t plus phi naught times the derivative of what's inside, which is omega again, and so it's minus omega squared a sine of omega t plus phi naught. And this is what we expected, because when we evaluate the acceleration and add it to omega squared times the position, which is omega squared times that, we have to get 0. And so that's perfectly consistent with what we expect. And so now we can calculate the position, the velocity, and the acceleration of the mass. So once again, I have this spring, right, and it's oscillating back and forth like this. And if you sort of imagine it going back and forth, it's going to the right, and it stretches out to its maximum. It stops. It changes direction as it goes in. It stretches in as far as it can, maximum, and so on. And so there are times where it's got all its energy is in potential energy because it's come to a stop. And there's times where all its energy is in kinetic energy. That is to say, the potential energy is 0 because it's at its equilibrium. That's when the velocity is at its highest, and so it's all kinetic energy in the middle. And so it goes potential energy, potential energy, kinetic energy, potential energy, and in between they're mixed. Well, we can calculate these things. We can say, look, the potential energy is 1/2 kx squared. That's equal to 1/2 k times a sine of omega t plus phi naught squared, right? And so that's 1/2 k a squared sine squared of omega t plus phi naught. The kinetic energy is given by this term. It's 1/2 m v squared, which is 1/2 m times, we have to go back to what we calculated for the velocity, right? And the velocity was omega a cosine of omega t plus phi naught, right? Squared. And so that's 1/2 m omega squared a squared cosine squared of omega t plus phi naught, right? Well, we already said that omega squared is equal to k over m. So m omega squared is equal to k, right? And so this becomes 1/2 k a squared cosine squared of omega t plus phi naught. Are you with me? I just replaced these guys with k, right? And now if you look at these two terms, right, if I say, I can say, look, the potential energy plus the kinetic energy, it's just they each have a 1/2 k a squared times sine squared of omega t plus phi naught. That's for this guy, plus cosine squared of omega t plus phi naught. These two terms, sine squared plus cosine squared, are the same thing. It's just 1. Or just 1/2 ka squared. So the mechanical energy is constant. If I calculate the potential energy, which is constantly changing, and the kinetic energy, which is constantly changing because this thing's getting stretched all the way out, a lot of potential energy, no kinetic energy, coming zipping through the middle, a lot of kinetic energy, no potential energy, and so on. If I add those two things up, I get just a constant 1/2 Ka squared for the total energy. And notice that 1/2 Ka squared is just the maximum potential energy. The potential energy for a spring is 1/2 Kx squared. Its maximum value is 1/2 times K times the maximum value of that X can have, which is the amplitude, A squared. Similarly, let me just, so that's, I'll just erase this thing. In other words, the total energy is the same thing as the potential energy when there's no kinetic, but I can also calculate the maximum kinetic energy. Which is just 1/2 times the maximum m times the maximum velocity squared, right? That's the maximum this is. But we already said in the last time that that V max is just omega times the amplitude, right? And so that's 1/2 m omega squared A squared. That's the maximum kinetic energy. But we just said a minute ago that omega squared times m is just K. Is just K. So the total energy is the maximum value potential energy can have, which is what happens when all of the energy is potential energy. It's come to a stop. Or I can say the total energy is the maximum energy kinetic energy. The kinetic energy can have. That's when it's at its equilibrium position, zipping through, going one way or the other, where its potential energy is 0 and its kinetic energy is at its maximum value. Those two values end up being the same, of course, just the total energy. So we're going to come back to the mass on a spring, but right now we're going to talk about the pendulum. And so the pendulum is a simple harmonic oscillator. If you pull out a pendulum and let it swing back and forth, it'll act like a simple harmonic oscillator. It'll swing to one side, and it'll swing to the other side, and it'll swing back and forth. The first pendulum clocks were designed by Galileo, who was sitting in church when he was a kid and noticed that the time it took to oscillate back and forth one time seemed to be independent of how far it was oscillating. That is to say, so they had chandeliers in the roof of his church, and they would open the windows at the top, and the chandeliers would rock back and forth, and on a windy day they would rock far, and then on a calm day they would rock a smaller range. And what Galileo noticed was he compared their pendulum to his heart rate, and he noticed that the oscillation was about the same time, even though the amplitude was much different. And so he began to study using pendulums as clocks because he was very interested in measuring time, as we know from his kinematics experiments. And so here's a pendulum, and we're just doing some, it's a simple pendulum is just a point mass at the end of a string, and we'll talk about a different kind of pendulum later. But so here's this mass, and you pull it up and you release it. And we're going to measure the arc length, that is to say how far it's fallen with the letter S, since there's not really a fixed coordinate system here. But at this point, we're going to do a free body diagram where the y-axis is lined up along the tension, and the x-axis is lined up perpendicular to that, this way, right? And then we're going to break these forces down. The tension is right along the y-axis, but if I take the weight, this becomes mg cosine theta, where theta is the angle of the pendulum, and this piece here is mg sine theta. And so it's the mg sine theta piece that moves the pendulum, causes the pendulum to rock, and then when it swings over to the other side, the component of tension along the arc is pointing back in the opposite direction again, and so it just rocks back and forth like this. This equation changes as theta changes because the angle is different, but all the variables look exactly the same. And so if I were to take this situation and write the sum of the forces in the x direction equals m a sub x, right? Well, the only force in the x direction is this one, and it becomes minus mg sine theta equals m a sub x. Well, a sub x is just the acceleration in the x direction, and so that's just m times d squared s over dt squared, right, where s is the distance along the arc. And so we can relate s to the angle. If you remember when we started talking about angles in radians, theta is equal to the arc length, which is in this case s, divided by the radius L. That's how we define the arc length in radians. And so the length along the arc is, that's how we define the angle in radians. The length along the arc is L times theta, where L is a constant. And so ds dt is just L times d theta dt, right? And d squared s over dt squared is equal to L times d squared theta over dt squared. And so this equation, which equates those two things, becomes minus mg sine theta equals m times d squared s over dt squared, or L d squared theta over dt squared. I can cancel an m from both sides, and this becomes d squared theta over dt squared plus g over L sine theta is equal to 0. If you remember, back when we had the spring, we had this. We had d squared x. So this is the pendulum. This is the spring, or simple harmonic oscillator. Well, if you're a mathematician, these look almost the same, where I've replaced theta with x, except and g with k and m with L, except here I have a sine theta, and here I just have an x. If this was just a theta instead, these equations would be mathematically identical. What we're going to show on the next slide is that, in fact, for small angles, sine theta and theta are approximately the same. This is a purely geometric argument. So probably shouldn't have erased my if you do a series expansion on sine of theta, which you probably saw in a math class at some point, it can be approximated by theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial, and so on, as you go up the law. And you can have an infinite number of those until you get it exactly, or as accurately as you want. And so if theta is very small, sine theta is approximately theta. So for example, in radians, theta equals 0.1 radians. That's about 6 degrees, right? And so sine of 0.1 radians is equal to 0.1 minus 0.1 cubed over 3 factorial plus 0.1 to the 5th over 5 factorial minus, and so on. Notice this term is 0.1 cubed is 0.001, and divided that by 6, which is what 3 factorial is 0.00016, compared to this is pretty negligibly small. It's well under 1% of that. And so at 6 degrees, I have an extremely accurate representation of sine theta by just using theta. Since most pendulums don't oscillate very far, even 20 degrees, this is a pretty good approximation just using theta. And so what we end up with in that equation I had on the previous page is d squared theta over dt squared plus g over L times theta is equal to 0. And now I'm right back to an identical solution for my simple harmonic oscillator as I had before. This is a sine of omega t plus phi naught, where omega is equal to the square root of g over L instead of the square root of k over m. And so a pendulum acts exactly like a weight on a spring, as long as the oscillation angle is small. If we make a pendulum that's length is 1 meter, then the period is 2 pi times the square root of 1 meter over 9.8 meters per second squared. Right. And that gives about 2.007 seconds. You can do other clever things. For example, you can use a pendulum to measure g. So if I rearrange this equation, I can say t squared is equal to 4 pi squared L over g, sorry, lowercase L over g, or g is equal to 4 pi squared L over the period squared. And so if you have a pendulum of known length and you just measure its period, it allows you to calculate g. And so again, that's a lowercase l. Let me try again on that one. So we can say, what is g if L is equal to this and the period is equal to this, right? And so if I evaluate that, I get g is equal to 4 pi squared times 0.75 meters over 1.7357 seconds squared, and I get 9.8281 meters per second squared. This is tricky because measuring periods this precisely is really difficult. You'd probably have to measure 1,000 oscillations or something, the time for 1,000 oscillations, and divide it by 1,000 or something like that. And you'd probably want to do it where there isn't much air resistance, so you might want to do it in a vacuum. But this is certainly one way you can use to measure the value of g at different locations. So what we had was we showed that the differential equation for position in a pendulum looks like this, where A is now, when we're doing the spring, A was the maximum displacement of the spring. In this case, A is the maximum angle. Right, if I pull it out to some initial angle, then the angle it's going to be at is that times sine omega t. It's going to oscillate back and forth. So if I pull it out to 3 degrees or whatever, 0.5 radians or something like that, that's what A is. And then this will allow it to oscillate back and forth between those. We just said a minute ago that omega is equal to the square root of G over L. And so that's the angular frequency. If you remember, omega is also equal to 2 pi over the period. Right? And so that means that 2 pi over the period is equal to the square root of G over L, or the period is equal to 2 pi times the square root of L over G. And so I'll get another sheet and do a few examples of this. So this relates the period to the length of a pendulum and the force and the acceleration of gravity. Notice a couple of things. The mass doesn't matter in here. And so for a simple pendulum, it doesn't, how fast it oscillates back and forth doesn't matter. Also, the period doesn't depend, as Galileo noticed, on the initial angle. All it depends on is the length and gravity. So if you pull it out any length, as long as the small angle formula is true, which means as long as it's smaller than 10 or 20 degrees, it'll oscillate at this period, which just depends on the length and the force of gravity and the acceleration of gravity. And so it'll oscillate differently on the moon, because the moon has a different gravitational acceleration, or it'll oscillate differently on the sun, or on Jupiter, or on Earth. But if the length is the same, it doesn't matter if it's a really tiny oscillation like this or a bigger oscillation like this. The only thing that's true is it has to be a small oscillation compared to 90 degrees, you know, and so that the small angle formula works. When we get to more advanced mechanics, we'll solve that problem without approximating the small angle formula, and that one gets a little harder. So I'll do a couple of examples of this on the next slide. So this is an example that's very similar to the pendulum, the simple pendulum that we talked about a minute ago, but this is called the physical pendulum. And so the black outline that looks like a chicken leg or something like that, it's just a random shape. And it's got a pivot point up here. So there's a hole drilled into it or something like that. And so it's like I was holding this thing like this, and it was free to swing back and forth like that. Right? And so it can pivot about this point. And so we want to know what the equation is of motion for this thing. And so I've drawn all the forces on here. Here's the center of mass of my chicken leg. And so if we just look at the forces acting not at the pivot point, the only one we have to worry about is gravity. And that acts at the center of mass. I've just picked a spot here and said that's our center of mass. And so the force that's acting at the center of mass is just mg. It's got a component that's along the line connecting the axis to the center of mass, connecting the rotating axis to the center of mass, and it's got a component perpendicular, just like we've always done. If we wanted to, we could draw our little coordinate system out there like this, like we did for the simple pendulum. But we're going to take a look at this one from the standpoint of torques, and so we're going to say we could have done this for the simple pendulum as well. We're going to say, look, there's a torque on this about this axis. There's a force this way, right? And so the torque is R cross F, except I have to do it with my right hand. Sorry, R cross F, right? R is going from the pivot point to the point of action of the force. The force acts at the center of mass. It goes this way. And so the torque is in the downward direction. It wants to rotate this thing clockwise, right? It's into the board. And so the magnitude of the torque of a cross product is just the magnitude of the R times the magnitude of F times the sine of the angle between them. And so R is if you remember from when we were doing torques, is the distance between the rotational axis and the point of action of the force. And so that's L, right? The force is mg. And and the torque depends on how big the angle is between those two. It's a maximum when the angle between the force and the line connecting the rotation axis to where the force is acting is at 90 degrees. In between is just multiplied by sine theta. And so this tells us the torque that's acting on this thing to cause it to rotate due to gravity, right? There are no other torques acting on it. All the other forces acting on this thing are acting at the pivot point, and forces at pivot points cause no rotation because their R is 0. And so if you remember, torque is a rotational equivalent of force, and so Newton's second law for rotational motion is torque equals I alpha. If you recall, that's similar to F equals ma for linear motion. This is the angular acceleration, this is the torque, and this is the rotational equivalent of mass. This is the linear acceleration, the mass, and the force, right? And so since the rotation is clockwise, the direction of our torque is into the board. It's a negative torque because it's going against the direction of the angle. And so we can say that if we want to say the torque is equal to I alpha, right, we can get the directions in by doing this way. Minus L mg sine theta is equal to I times the angular acceleration, and that's I times d squared theta over dt squared. This is the equation for the angular acceleration, right? Acceleration is d squared x dt squared. Angular acceleration is d squared theta dt squared. So this is that thing that's the rotational inertia. And when we did it for like a sphere, or it was 2/5 mr squared, or for a hollow sphere, that was a solid sphere. For a hollow sphere, it was 2/3 mr squared. For a cylinder, it was half mr squared, a solid cylinder, and so on. Maybe we don't know what I is. It could be anything, right? It depends on the shape of this object and where its mass is located. But this equation, if I now combine these two, I get I times d squared theta over dt squared equals mgl sine theta, sorry, with the negative sign in front of it. And so I can rewrite this as d squared theta over dt squared plus mgl over I times sine theta is equal to 0. And you can see this is looking exactly like the simple pendulum problem, where we get a second derivative in theta, some constant that depends on sort of the physicality of the problem, and then a sine theta here. And so for small angles, by the way, I talked in the last when we were doing simple pendulums about the small angle formula, and I showed it by doing a series expansion of this. There are lots of demonstrations that this statement is true. Some are just simple geometric arguments, and I think they're in your textbook, but you can Google them. There are lots of ways to show that for small angles, sine theta is approximately theta. So if you hadn't seen the series expansion versions of that, you might look at another one, and they're pretty simple, based on just how angles are measured in circles and stuff. And so then I'm back to this. I'm back to d squared theta over dt squared plus mgl over I times theta is equal to 0. And this is the same differential equation we've been doing it. We did it for the spring, we did it for the simple pendulum, and now we're doing it for this one. We say omega is equal to the square root of mgl over I. It's the square root of whatever is multiplying this thing, and then we get theta is equal to, and you can put a here, that's what I've been putting. I think your textbook puts this, theta naught, or theta, maybe theta max. Anyway, it's the amplitude. You can still use a there if you want. Sine of omega t plus phi naught, or phi. It's the exact same solution that all the others have. It's just an oscillatory motion, and in this case, this is 2 pi over the period, right? And so you can solve for the period for this case as well, depending on what the rotational inertia and the distance from the center of mass, the rotation axis, and so on. You can just plug into those and solve. And so it's just another example of a simple harmonic oscillator with a more complex pendulum.